Welcome to the next episode. Today, we will begin building the sorting functionality for the inventory and the storage box. Our goal is to enable sorting by name, type, weight, and quantity, both in ascending and descending order. Since this is a complex feature, the series will be divided into multiple episodes. Before we jump into the BPC inventory, we need to fix a small issue from the previous episode in the MyPlayer controller. In the isInputKeyPressed function, ensure that the return value connected to the for each loop completed execution pin is set to false. This ensures that the function correctly returns a value if no matching input key is found. Once that is done, save the changes and close the player controller. Now, navigate to the Inventory System folder in the Content browser and create a new folder named Data. Open this folder and create another folder inside it named enums. Inside the enums folder, right-click, navigate to the Blueprint menu, and create a new enumeration. Enumerations allow us to define a set of specific options that can be used throughout the project, which is especially useful when building sorting features like this one. Name this enumeration E_sort items by and open it. Use the +@enumerator button to create 4 enumerators. These will represent our sorting options. The first will be name, the second type, the third weight, and the fourth amount. Alternatively, you could use quantity for the last one, as it may fit better, but during the implementation, I used amount, so we will stick with that for consistency. Save and close the enumerator. Next, return to the Inventory System folder and move the Structures folder into the newly created Data folder. This helps keep the project well organized by grouping related files together, making it easier to manage as the project grows. Now, open the BPC_inventory blueprint. Let us get started with the actual sorting function. Open the event graph to ensure we all begin from the same point. Create a new function named Sort Items by Amount and place it in the Sort category. Mark the function as private to prevent it from being accidentally accessed or called from the wrong place later. This is a good practice to avoid unintended behavior and errors. The function requires 2 input values. The first input is named sort by, and its data type will be the E_sort items by enumerator we just created. Enums are useful here because they allow us to handle predefined sorting options clearly and consistently. The second input is named ascending sort order and has a data type of Boolean, which determines whether the sorting will be in ascending or descending order. Save your progress before moving forward, and we can now dive into implementing the function. We have 4 sorting options that work with 2 different data types. Name and type will be sorted using the string data type, while weight and amount will be sorted using the number data type. In this function, we will focus on sorting by numbers, so we need to determine which sorting method is requested using the sort by pin with a switch on E_sort items by. Next, drag the item slots array into the graph and use the last index node to get the last index of the array. This gives us the upper limit for our sorting loop, which is crucial for iterating through all items. Then, search for the for loop node. This node will handle the iteration over the array. Connect the execution pins for weight and amount from the switch on sort items by to the for loop node, as these are the sorting options we are addressing now. Name and type will be left unhandled for now since they require a different approach. Connect the result of the last index node to the last index pin of the for loop node. Set the first index to 1, as we will start from the second item in the list for comparison. We will use the bubble sort algorithm to handle the sorting, which works by repeatedly comparing and swapping adjacent items in the list based on the requested criteria. This algorithm is simple and works well for smaller datasets. Take the name execution pin from the switch on sort items by and search for the print string node. Connect the type execution pin to the same print string node. Next, grab the inString pin of the print string node and search for the append node. In the A pin of the append node, write the following text. Sort is not supported by. Include the colon and space. Now, take the sort by pin from the function and connect it to the B pin of the append node. Unreal Engine will automatically insert the enum to string node between them. This will convert the enum value into a string representation, which allows us to dynamically include the sorting type in the message. With this setup, the print string node will display a message indicating that sorting by name or type is not supported by this function, meaning there was an incorrect call in the logic. While this step is not strictly necessary, it can be incredibly helpful for debugging, as it allows you to quickly identify where and why an unsupported sorting type was used. If everything is implemented correctly, this print string should never be executed during normal gameplay. Let us continue with the for loop node. Take the index pin and promote it to a local variable named index counter. This variable will track the current index during the sorting process and can be reused in other parts of the logic. Next, drag the index counter variable into the graph and search for the greater operator node. Connect the result of this node to a while loop node. Make sure to connect the execution pin from the previous node to the while loop node. This ensures the loop continues as long as the condition defined by the greater operator evaluates to true. Next, take the execution pin from the while loop and create a branch node. Then, drag the item slots array into the graph and search for the swap array elements node. Connect the true execution pin of the branch to the swap array elements node. This node allows us to swap two elements in the array. Now, take the index counter local variable and connect it to the first input pin of the swap array elements node. Then, drag another pin from the index counter variable and search for the subtract node, setting it to subtract 1. Connect the result of the subtract node to the second input pin of the swap array elements node. This is why we started at index 1 initially. If the value at slot 1 is greater than the value at slot 0, the two slots are swapped. Next, drag the index counter local variable into the graph again and search for the decrement int node. Connect the execution pin from the swap array elements node to this decrement int node, reducing the index after a swap. Now, copy both the index counter and the decrement int nodes and paste them near the false execution pin of the branch. Connect the false execution pin of the branch to the decrement int node that you just added. This ensures that even if no swap occurs, the loop decrements the index to continue iterating through the array. Let us recapitulate this briefly. First, we set up the index counter. The index pin of the for loop is promoted to a local variable named index counter to track the current position during sorting. Next, we set up while loop condition. The index counter is connected to a greater operator node, checking if it is greater than 0. The result is connected to a while loop, ensuring the loop continues as long as this condition is true. Then we added a branch for comparison. This allows a condition to be checked during each iteration. What we will set up is next. Then the swap array elements. If the condition is true, the swap array elements node is executed. The index counter is used for the first input pin, and the second pin is connected to index counter 1 via a subtract node. After a successful swap, the index counter is decremented using a decrement int node, connected from the execution pin of the swap array elements node. If the condition in the branch is false, the index counter is still decremented using another decrement int node connected to the false execution pin of the branch. This setup ensures that the array is iterated through and sorted correctly by swapping elements as needed and continuously reducing the index to move through the array step by step. Now, let us set up the condition for the branch. First, clear some space in the graph to keep things organized. Drag the item slots variable into the graph and use the getAref node to access a specific element. For the index of this get node, use the index counter variable to dynamically target the current element. Next, take the result of the get node and create a break node. Hide all the pins on the break node except for the quantity pin, as that is the only value we need for this condition. Now, copy these four nodes, item slots, getAref, index counter, and break and paste them below. In this new set, make one adjustment. Connect the index counter variable to a subtract node set to -1. And then connect the subtract node to the index pin of the second getRef node. This allows us to compare the current element with the previous one. Finally, take the quantity pin from the first break node and connect it to a greater operator node. Then, connect the quantity pin from the second break node to the other input of the greater operator node. This condition will check if the current item's quantity is greater than the previous item's quantity. Bring the getSort variable, the input of the function, into the graph and connect it to a select node. This select node determines which comparison logic to use for sorting. Since we have currently implemented the sorting logic for quantity, connect the result of the greater operator node to the amount pin of the select node. If you named your sort by enumerator quantity, it will appear as such in the select node. The name and type pins remain unconnected, as we excluded these options earlier. We will handle the weight pin later. Next, bring the getAscending variable into the graph and connect it to another select node. Take the return value of the first sort by select node and connect it to the false pin of this ascending sort order select node. For the true pin, take the return value of the first sort by select node, negate it using a not bool node, and connect the result to the true pin of the second select node. This ensures the sorting order is inverted when descending order is selected. Finally, connect the return value of the ascending sort order select node to the condition pin of the branch node. This completes the dynamic selection and sorting logic based on the user's input. This concludes the first part of this episode. Next time, we will continue and finalize this function. We will implement the sorting logic for weight, address additional considerations that may arise during sorting, and fully complete the sort items by amount function along with the necessary event to trigger it. If you found this episode helpful or enjoyable, consider leaving a like or subscribing to the channel so you do not miss future episodes. If you have suggestions or requests for features in the inventory or other tutorials you would like to see, feel free to share them in the comments or on the Discord server. If you need help, you are welcome to join my Discord server, and I will gladly assist you. See you next time.